Hey there, so I just finished this absolutely fascinating book called Algorithms to Live by the Computer Science of Human Decisions by Brian Christian and Tom Griffiths, and honestly, it's totally blown my mind. You know how sometimes you feel like life is just a never-ending series of tricky decisions? From the tiny everyday choices to the huge life-altering ones, well, this book dives deep into that feeling, but it comes at it from a really fresh angle. Computer science. It sounds a bit dry, right? Like, what can a bunch of lines of code teach me about picking a partner or cleaning my closet? But trust me, it's anything but. The core idea here is that computers for decades have been tackling problems that are strikingly similar to our everyday dilemmas. Think about it. How does your phone decide which apps to keep running, or how much memory to use, or when to switch between tasks to keep things zippy? Those are all problems of optimization and efficiency, and computer scientists have come up with elegant, provably effective solutions for them. The authors argue that if we understand how these algorithms work, we can actually apply them to our own lives and make smarter, more rational choices. It's about designing algorithms for humans, and it's backed by logic, not just anecdotal advice. One of the first big ideas they unpack is optimal stopping. Have you ever been, say, house hunting or looking for a parking spot, or even trying to find the one when dating? You're constantly asking yourself, should I take this option or keep looking for something better? It's a classic problem. The book explains something called the secretary problem, which is about choosing the single best option from a sequence of possibilities where you can only evaluate them relatively. And once you pass one over, you can't go back. Turns out the optimal strategy for this, if you don't know anything about the pool of options beforehand, is often the 37 rule. You look at the first 37 of the options without committing, just to get a sense of the range. And then you pick the very next one that's better than anything you've seen so far. It's wild. Michael Trick, a real professor, even applied this to his whole love life, and it helped him decide when to propose. But what if you can get rejected or go back to someone? The book explores those variants too, showing how even a slightly different setup changes the optimal strategy. For example, if you have a 50-50 chance of rejection, you should start making offers after just a quarter of your search. It really makes you think about how we often just swing these big decisions, when there's actually a mathematical foundation for making them better. Then there's the explore-exploit trade-off. This is super relatable. Imagine you're trying to pick a restaurant. Do you go to your favorite Italian place, which you know is great exploit? Or do you try that new Thai place that just opened? Explore? This tension is at the heart of so many daily choices. The computer science term for this is the multi-armed bandit problem, like walking into a casino with a bunch of slot machines and not knowing which one pays out best. The key insight here, through something called the Giddens Index, is that you should actually give a significant exploration bonus to things you know less about, especially if you have a long horizon or lots of time ahead. This explains why kids are so exploratory. They should be, because they have their whole lives to learn what works best. But as you get older, the balance shifts and it becomes more rational to exploit your known favorites. This concept also underpins things like A/B testing on websites, where companies experiment with different button colors or headlines to see what works best. And even more powerfully, it's changing how clinical trials for new drugs are designed, pushing for play-the-winner algorithms that adapt during the trial to give more patients the better treatment, rather than strictly sticking to random assignment. It highlights that sometimes simply trying to minimize regret, rather than always picking the absolute best, is the most effective approach. Speaking of organization, have you ever worried about how messy your desk is, or whether you're sorting your emails correctly? The book delves into sorting and caching. Computer scientists are obsessed with sorting because it's at the heart of what computers do. They even have a shorthand for measuring an algorithm's worst-case performance called big O notation. So you know how some sorting methods like bubble sort or insertion sort, imagine sorting books one by one on a shelf, are really slow for large numbers of items? They get exponentially worse as the number of items grows, but the book reveals a surprising truth sometimes. The most efficient thing to do is not to sort at all. This is the sort-surge trade-off. For example, a study found that people who spend less time organizing their emails actually spend less time overall looking for them later. compared to those who meticulously filed everything. Why? Because the time spent searching was less than the time spent filing. It's like the no-pucci filing system, where you just put everything on a pile, and the most recently used items end up on top. The self-organizing pile is actually optimal if you access things based on how recently you used them, a principle called a release recently used that computers use in their memory caches. Our own human memory works similarly, tuning itself to the patterns of our environment, effectively caching what we're most likely to need. It's a wonderful thought. Your messy desk might actually be a perfectly optimized system. Then we get into scheduling. And let's be honest, who doesn't need help with that? The book highlights that all the time management gurus have different advice, that the key to scheduling, like so many other things, is to first define your goal or metric. If your goal is to minimize your maximum lateness, the optimal strategy is earliest due date, do what's due soonest. But if you want to clear your to-do list as fast as possible, its shortest processing time, do the quickest task first. The book even suggests that our tendency to procrastinate on big tasks by doing small, easy ones might actually be as optimizing for the wrong metric, trying to reduce the number of outstanding tasks as quickly as possible. Even if it means putting off the important things, the sobering news is that most real-world scheduling problems are actually intractable for computers to solve perfectly, meaning they're just too complex to figure out the absolute best sequence. And here's a bit one: context switching. You know how programmers say interruptions kill productivity? Humans have significant context switching costs too, losing minutes not microseconds every time we switch tasks. So multitasking, far from being efficient, can actually be thrashing your productivity. The solution: interrupt coalescing, batching similar small tasks like paying all bills on one day or checking email only once a day. It's why Donald Knuth, a legendary computer scientist, hasn't had an email address since 1990. He batch processes his life to avoid constant interruptions. Another fascinating chapter is about Bayes' rule and predicting the future. We often have to make predictions based on small data like how long a new relationship will last or how successful a new movie will be. The book explains the Bayes' law, which offers a surprisingly simple formula for this. If you've seen W successes and then attempts, your best guess for the future success rate is W1 and 2, and then there's the Copernican principle, inspired by J. Richard Gottlieb, who, standing at the Berlin Wall, realized he could predict its remaining lifespan based on how long it had already existed. The principle suggests that the best guess for how long something will last is that it will continue for as long as it already has. This is because, without other information, you assume you're observing it at a random point in its existence. This idea helps explain why things that have been around for a long time, like human lifespans or some types of poems, are likely to continue longer, while others like movie running times or technologies are more likely to end soon if they've already gone on for a seemingly long time. It even offers a powerful insight into how Stephen Jay Gould, when diagnosed with cancer, found solace in understanding the distribution of survival times, realizing that the median didn't tell the whole story. The crucial takeaway here: we need to protect our priors, be careful what information we let in, especially from the news, because it can skew our perception of reality and lead to bad predictions, which leads perfectly into overfitting or when to think less. It sounds counterintuitive, right? Charles Darwin famously made a pro and con list to decide whether to marry, but the book argues that more thinking, more data, and more complexity aren't always better. In machine learning, overfitting happens when a model is so perfectly tuned to the past data it's trained on that it fails to generalize to new, unseen data. It's like designing a strategy specifically for one specific test, rather than learning the underlying subject. The book calls it an idolatry of data. This shows up everywhere in our taste buds, getting us to like unhealthy foods, overfitting to immediate pleasure. In sports where athletes optimize for quirks and scoring rules rather than true skill, and especially in business, where poorly designed incentives can lead employees to ruthlessly and cleverly optimize the wrong thing. To combat overfitting, computer scientists use cross-validation testing models on data they haven't seen. and regularization penalizing complexity in models. This leads to the idea of early stopping. Sometimes, giving yourself less time to decide or less data to consider actually forces you to focus on the most important factors, leading to better, more robust decisions that generalize well. It's a reasoned argument against reasoning too much. So, if most complex problems are intractable, what do we do? The answer, says the book, is relaxation. When computer scientists face a problem where finding the perfect solution is essentially impossible, like planning the optimal wedding seating chart, or the traveling salesman problem for a million cities, they relax the problem. This means temporarily making it easier. One way is constrained relaxation, where you remove some of the rules and solve the problem you wish you had. It's like asking, what would you do if you weren't afraid? Another is continuous relaxation, turning discrete choices like putting a fire truck in this spot or that spot into a continuum, putting half a fire truck somewhere, then rounding. And my favorite, Lagrangian relaxation, turns impossibilities into mere penalties. Instead of you must do this, it's you can do this, but it will cost you. Think about a rock band playing past curfew and just accepting the fine rather than cutting their set short. The beauty is that while these don't guarantee the perfect answer, they often give you a solution that's good enough and often dramatically faster to find. It's about being consciously driven by wishful thinking to tame seemingly unmanageable challenges, and on top of that, sometimes the best solution is to embrace randomness. It sounds wild, but the book highlights how randomized algorithms can actually outperform deterministic ones for certain problems. The Monte Carlo method, for example, which was used during the Manhattan Project to simulate nuclear reactions, came from a mathematician named Stan Ulam trying to figure out the probability of winning a game of solitaire. Instead of trying to calculate every single possibility, which is mind-bogglingly complex for solitaire or for something like healthcare reform, he realized you could just play the game many times and observe the outcome. This is sampling, and it's surprisingly powerful for cutting through complexity. Even for yes or no questions, randomness also helps algorithms avoid getting stuck in some local maxima when searching for solutions, like when using simulated annealing to design better computer chips, and it even extends to creativity. William James, the father of American psychology, believed randomness was at the heart of creativity, generating new ideas that the environment then selects. So, something as simple as using Brian Eno's oblique strategies cards, or picking a random article on Wikipedia, or even joining a sea farm that sends you unexpected vegetables, can help jitter you out of your comfort zone and lead to new discoveries. Just don't go full dice man and make every decision randomly. Finally, the book looks at networking and game theory, which is all about the problems we create when we interact with each other. You know how when you're on a phone call, you're constantly saying uh-huh or yeah to let the other person know you're still there and listening? The book argues these human bacchanals are exactly like X acknowledgement packets in computer networking. Without that consistent feedback, the sender slows down, just like the internet's TS protocol slows down if it doesn't get X. This can lead to buff brute, where too much data piles up in invisible queues, causing delays. And in game theory, they look at problems like financial bubbles, which are often driven by people trying to anticipate what average opinion expects the average opinion to be. The sobering truth is that many real-world games, and finding their Nash equilibria stable strategies where no one player wants to change their move, are intractable for computers and for us. This means that even rational players can end up in really bad outcomes, like the tragedy of the commons where everyone acting in their own self-interest collectively ruins a shared resource. But the book ends on an incredibly profound and hopeful note with computational kindness. This is the idea that we should design systems, and even our interactions, to minimize the computational burden on others. Imagine trying to make change with an 18-cent piece. It would minimize the number of coins, but computationally it's a nightmare for the cashier. Or when a friend asks, "What do you want to do tonight?" saying "I'm flexible" seems kind, but it actually passes a huge computational burden to the other person. forcing them to simulate your preferences. The authors argue for systems like the Victory auction, where the highest bidder wins but only pays the second highest bid. Why is this awesome? Because honesty is the dominant strategy. You don't have to strategize or try to guess what others will do. Simply bidding your true value is always the best move. No matter what anyone else does, the game itself optimizes for you. Ultimately, Algorithms to Live By isn't just a collection of cool computer science facts, it's a completely new way of thinking about ourselves and the world. It teaches us that true rationality isn't about perfectly calculating every outcome, which is often impossible anyway, but about choosing the right algorithms for the right problems. It's about accepting good enough solutions when perfection is out of reach, understanding the hidden costs of our choices, and being mindful of the computational burdens we place on others. It makes you realize that by thinking like a computer scientist, not in a cold, rigid way, but in a way that understands efficiency, trade-offs, and the limits of knowledge, we can actually live more wisely, reducing friction and gaining clarity in our wonderfully messy human lives. It's truly transformative.